Picture a mountain in Iran. From above there is nothing to see. No buildings, no roads, no movement. Satellites show bare rock. Radar shows bare rock. Human eyes show bare rock. Yet 80 meters beneath that granite sits a nuclear facility Iran spent 25 years building. Iran did not rely on camouflage. It relied on physics itself, burying the facility under hundreds of meters of stone meant to absorb, deflect, and destroy any incoming weapon long before it could reach the chambers carved out far below the surface. But hiding a facility behind rock creates a problem Iran never fully escaped. You can conceal a structure, but you cannot conceal that it exists. Everything running inside, machinery, fans, generators, even footsteps, pushes faint signals upward through the surrounding stone continuously. This is how Israel effectively sees through mountains, and why Iran's most guarded underground sites were never quite as invisible as their builders assumed. The core question: how do you map a hidden interior without drilling, entering, or being noticed at all? The answer draws on 4 branches of physics working together, each targeting a different weakness the mountain cannot hide. Individually, they reveal fragments. Combined, they produce something close to a complete picture of what lies beneath the surface. Rock is never truly silent. Any machine running underground creates vibration, radiating outward through solid stone as seismic waves. By the time these reach the surface, they are astonishingly faint, millions of times weaker than a genuine earthquake and easily lost in noise. Israel's answer is arrays of sensitive seismic sensors spread across the surface above a suspected site. Multiple sensors, placed at carefully chosen distances, each catch the same underground vibration at a slightly different moment, and those timing differences become the key. A sensor directly above the source detects the wave first, one farther away detects it later. Software compares arrival times across the array and triangulates the vibration's exact origin, much like GPS triangulates location using radio timing instead of seismic timing. Heat is the second unavoidable byproduct of underground activity. Machinery generates warmth that has to travel somewhere. Ordinary thermal cameras cannot see through 80 meters of rock. The heat fades far too much across that distance to register on infrared. Synthetic aperture radar takes a different approach. Rather than searching for heat directly, it searches for what sustained heat does to the ground above it, since underground warmth slowly conducts upward and subtly expands the rock nearer the surface over time. Warmed rock expands by fractions of a millimeter, invisible to any camera or human eye. Satellites bounce radar pulses off the ground, comparing images captured weeks or months apart to detect surface shifts smaller than a millimeter with remarkable consistency. Radar reveals more than location. It reveals whether a facility is truly running. Active sites generate heat and expand. Dormant sites cool and contract. Tracking these shifts over months lets analysts judge operational status even when officials claim otherwise entirely. Before the strikes of June 2025, radar analysis of the Fordow site reportedly showed steady thermal expansion consistent with ongoing operation, even as Iran publicly stated enrichment had been paused. The rock told a different story than the statement. The third method exploits something counterintuitive. Empty space weighs less than solid rock, and that difference in mass is detectable. Earth's gravitational pull is not perfectly uniform. It varies slightly depending on the density of material beneath any given point. Dense granite pulls slightly harder than an empty tunnel of the same size. A sensor above a hollow chamber 50 meters down registers marginally weaker gravity than one above solid stone. Older gravimeters were too crude to catch such a faint signal. Quantum gravimeters change that. Built on principles borrowed from quantum computing, they track laser-cooled atoms in free fall, since their exact rate of drop is influenced by gravity beneath them, allowing precision fine enough to trace buried tunnels and chambers. Combine all 3 methods, and the picture sharpens. Seismic arrays reveal what machinery is running. Radar reveals where heat has built up over time. Quantum gravity mapping reveals the physical shape of every void, active or entirely dormant, beneath the surface. A fourth, unavoidable vulnerability is shared by every underground facility: ventilation. People need breathable air and equipment needs cooling, so air must continuously flow in and out. Wherever that exchange happens, it carries a temperature signature the surrounding rock lacks. Exhaust air leaving an underground facility runs warmer than the surrounding surface, simply because the facility generates heat that ventilation continually removes. At whatever point this air escapes to the surface, it is measurably warmer than the rock immediately around it. Modern infrared satellites can resolve ground temperature differences as small as 1/10 of a degree Celsius from orbit. Exhaust air escaping several degrees warmer than its surroundings is not subtle to such instruments. It functions essentially as a thermal beacon. Iran reportedly disguised several exhausts inside natural rock crevices and beneath scattered debris, which reduced their thermal visibility, but did not eliminate it. Warm air flowing through a crevice produces a distinct thermal spread pattern differing from unheated rock formations. Put together, the full detection system relies on 4 independent physics-based methods, each exploiting a property the underground facility cannot eliminate. Seismic arrays map internal activity, radar maps accumulated heat, gravimeters map physical structure, infrared maps life, support ventilation. Each method carries its own limitation. Seismic detection needs the facility to be actively running. Radar analysis requires weeks of comparative imagery. Gravity mapping typically requires low-altitude passes. Infrared detection only works while ventilation systems push warm air outward. Used together, these 4 independent data streams cross-reference one another and gradually assemble a remarkably complete picture, not despite the mountain's rock, but through it, turning the stone meant to provide protection into the medium that exposes what lies hidden. Iran invested enormous resources burying key facilities deep underground specifically to keep them concealed from Israeli intelligence. The facilities were, in a literal sense, hidden from view. Yet the intelligence apparently found them anyway, not through spies, but through applied physics. Fordow was engineered to be effectively unbombable. 80 meters of granite overhead, reinforced blast doors, and redundant backup power throughout. Officials described it as indestructible. But before anyone could ask whether a weapon could reach it, a more basic question needed answering. Rock cannot fully protect what operates beneath it, because rock conducts seismic vibration, rock expands measurably when warmed, rock has mass that an empty tunnel does not possess, and rock still lets warm ventilation air escape wherever the surface is eventually breached. The mountain Iran chose as its shield turned out to be, quietly and continuously, one of its most detailed informants. Locating the facility and mapping its interior is only the first half of the challenge. The second half concerns how such depth is destroyed. That second half involves the GBU-57 massive ordnance penetrator, examined in full engineering detail, how it burrows through solid rock, how it determines the precise moment to detonate, and why the contest between unbombable bunkers and bunker-busting weapons has continued for 3 decades.